Welcome, everybody, and thank you for inviting me to talk at this workshop. My name is Neil Ferguson. I am from a little consultancy called Sine Nomine Associates. If anybody knows Latin will recognize that the name of the company means the company without a name. That's because we have two co-owners who were classics majors who couldn't agree on a name when they went to register the company. So we're stuck with that, and we ever deal with is able to pronounce the name of the company the first time, so it's always a long explanation of what's happening. My background is I'm a long-term maintainer of the S390X port of the Meadow JIT. Now, if anybody's not familiar with S390X, it's the IBM mainframe. So I look after the very big end of town when it comes to Meadow and the JIT. I started working on it in 2003 and have been working on it since, and ultimately have worked with both IBM and Microsoft to have .NET include this architecture as part of its community release. So a lot of big work, end of the town work, but also have done a lot of work on embedded systems and as well as the typical Intel systems. For example, a few years ago, we added AOT, ahead of time compiler support, to the SH4 platform for a client. Technically, it was a lot of fun. We learned a lot of things about the platform you never learned before doing low-level stuff. Also provide a number of runtime support to a number of clients. So people running Mono in their production environments, they want support for the Mono runtime, we do that. I had lived in the US for 20 years up until 2019 when I returned to Australia. But as you can tell, this accent is definitely not American. It's a strange one, and it's coming to you from southern Queensland at the moment, where it's just going about 10 o'clock at night. So if I start to drift off, please forgive me. I began working on this current project for the Wilderness Labs folks in early 2021, and if anybody hopefully saw Mark Stevens' presentation there, he gave a great in-depth description of Meadow and the type of stuff that we are involved in. So what they brought me on board for, because of my past experience with JITs and stuff, was to provide ahead-of-time compiler support, and that requires the ability to use DLOpen to bring in dynamic objects. And so the first thing I did when I looked at doing this was try to DLOpen with such an object and saw that it did not work with NUTX, or at least the level of NUTX we're running. And I think Mark indicated yesterday, we're running a little bit back level from what's current. So there are going to probably a few things I say here about support within NUTX. You're going to say, well, yeah, that's there now, but this is all coming from the point of view of the NUTX that we started on and have been working on since. So I quickly found out that we needed to expand DLOpen support to be able to support this ahead-of-time compilation. And that also involved additional relocation types that currently weren't supported within NUTX. We also needed to provide some limited external reference resolution, such that if the AOT module had references to things like printf or memcopy, we were able to resolve those at runtime. What we didn't need and what it didn't provide is support for nested shared object dependencies, such that if my shared object had a reference to another shared object, I won't go down that track to be able to provide that resolution. So it's very much focused on what was needed for this one particular application. So it is certainly not a general purpose solution, but hopefully it's something that could be turned into a general purpose solution with a little bit of effort. So again, for those who did not see Mark's presentation yesterday, I'll just quick single or couple of slides talking about the Meadow environment. So Meadow is a complete Internet of Things platform with defense-grade security that runs a full .NET standard. So applications run on our embedded microcontrollers. They're developed using the same type of tools that people running on the desktop. So you're running Visual Studio or VS Code. you're deploying to these devices, you're debugging these devices all from that IDE environment. We provide a complete plug-and-play Internet of Things library with a huge library of peripheral drivers, industrial control, graphics, DisplayPort, etc. This means that the application developer is strictly worried about functionality of the device rather than having to go down and plumb at the very basic levels there for you. So what we're trying to provide the application developer with is an environment where they can write code such as this and have this type of thing work with the devices. So as you can see, all the application programmer is worried about is purely functionality and letting the Meadow Foundation and Meadow Core libraries take care of all the bits and pieces. So the motivation for this, my part of the operation, has been speed. Mono is used to drive these applications on the F7 board, which is running the Thumb2 instruction set. Now, Mono itself had no JIT or AOT capability for the Thumb2. It certainly has an ARM support, but currently had no Thumb2 support, so that speed became a big issue. So, for example, we have the two boards running the same application here. Just keep your eye on the pictures in the little LCD screen in each of these boxes. On the left-hand side is one running without our JIT AOT support, and on the right is one with it. So just quickly note the pictures at the bottom when this thing starts. And the JIT application is finished. The interpreted application is still running. And running. And there it goes. So the motivation for providing JIT AOT was the speed up requirement to be able to run some of these time-sensitive applications very quickly. Now, in interpreted mode, there are a number of applications that are quite happy to run interpreted mode. So our use case is we're using the F7 device, we're using Mono to run these .NET applications. Initially, everything's running in interpreted mode, so to provide the increase in speed so that these applications that are time-sensitive, we needed to provide a JIT and/or an ahead-of-time option. Now, the ahead-of-time option requires the ability to load .so objects. So when you build these things, you end up with these shared libraries. These libraries need to be loaded by Mono and connected to and accessed. Currently, NutX only supports the relocatable file style of objects, so that when you run DL open, it actually does an explicit check. Is this an ET-rel object? If not, return saying cannot do. So as I mentioned, Mono already has ARM64 support, but to provide a JIT facility, we needed to provide the underlying code that's going to produce the Thumb2 instructions. There are a couple of options to this. We can start from scratch and create a whole series of runtime files that implement the Thumb2 ABI, etc. Or we reuse existing code in there and throw in a few if-defs, and we wanted to keep this as a minimum. So that's the option we chose. So we're using the same Mono drivers that they use for ARM, not ARM64, obviously. So the macros that they created to issue the instructions are reused, so we didn't have to create a whole heap of other things and extra code. We used the same trampoline code, and we're handling both 32-bit and 16-bit instructions. And this is the big change from Mono's existing ARM support, where everything is 32-bit. So there's a lot of assumptions of alignment and things like that. So a lot of work went into handling those cases. We also needed to cater for the differences between ARM and Thumb2 instructions. So certain instructions are available in the ARM environment that aren't available in the Thumb2 environment. And I think we had a reference to that in yesterday's first presentation of the workshop. In addition, there are a couple of instructions that do exist in Thumb2 that don't exist in ARM that became quite useful, just off the top of my head, was the floating point rounding instruction, VRND, I think, that actually proved very useful in the mono environment. There are also register restrictions, such that certain registers can't be used in certain instructions. There seems to be a lot of differences or restrictions on using the instruction pointer, the stack pointer, etc., when in certain instructions. Displacements are different. The maximum size in an ARM environment is different to the maximum size in a thumb2. And conditional instructions, the if then, else type of instructions have to be used in the thumb2 environment that aren't used in ARM. So there are a whole lot of issues to get this support happening. We needed to provide a JIT capability so that the AOT could be generated using the stuff that JIT put out, etc. There are two other options when creating a ahead-of-time compiler. You can use the LLVM in two modes, LLVM and LLVM only, which use the Clang compiler to generate the thumb instructions, etc. So we've got those three capabilities here, but the JIT we provided first because it works without even needing an ahead-of-time capability and provides a certain speed up to the application developer. So just to give you an idea of how this all fits together, once your application's built, you end up with a series of DLLs, MS Core Lib DLL, your application DLL, and certain other class library DLLs there. And their footprint is rather huge if you leave them by themselves. Obviously the MS Core Lib is very, very big because it has the core of .NET running there. But your application itself doesn't use a whole lot. And it seems pointless to load in megabytes of code onto your small board just for the purposes of running the application. So what we do use is the mono linker to shake out only that which is necessary within the application and creating a much smaller footprint there. So we take those big DLLs, we run it through the linker, we end up with some smaller DLLs that we put into a directory. And at this point, we can then perform the ahead-of-time processing. And as I mentioned, we can run it in one of three modes. And in this instance, we're going to be running it in the just-in-time compiler mode. And what that means is Mono will start up, will pull in the application and generate the machine instructions and point Mono at them, or point the AOT part of Mono at them, and it will then generate the necessary object decks, which will then link them and ultimately produce .so files. So after the process finishes, you end up with .so files, and you can look at them through the readelf command, and you can look at the headers and get an idea for what the requirements are in terms of the size of the text areas and the data areas. The other thing we're interested in now, because we're using dynamic objects, is the dynamic symbol table. And here again is one difference and one shortcut we have been able to make for our support for loading these objects. Mono's AOT objects are fairly self-contained. They don't have a large number of external or exported symbols. They basically have one that they're interested in. And this one is mono AOT file info. And what the loader does is take that information, that address, and we'll be able to locate a whole lot of information about the object itself and all the methods that live within that object. So we don't have to worry about exporting a lot of symbols and then creating updating the PLTs and GOTs and all those type of things you generally need to do with shared objects. So again, an expedient thing for us to do, which precludes it from being totally general purpose. So again, here's what Mono's doing when it loads an application. It will go there and have a look to see if these .so files exist. And we'll go and find if mscorelib.dll.so exists on your file system. And if it does, we'll try and issue a DL open request for it. the moment, well, prior to this support, it would fail because you define an object with an ET DYN type in its header. So what this support has done is been able to add this ET DYN support. So what we do now is we read the header and determine if it's an ET-rel or an ET DYN object. If it's an ET-rel, then we just palm off to the existing code that lives in the system to take care of what it does already. If not, we go and perform our functions, and I'll give it a schematic shortly, but just in brief, we're loading the text and data area, we're performing relocations, and we're resolving any external references. So diagrammatically, it looks like this. So item 1 down the bottom here, we have the shared object living on the file system containing the ELF headers, the relocation table, symbol tables, and relocation information, as well as the text and data sections. So our code will go in and read those ELF headers and determine how much space is required to load the object, the executables, and the data area in for that particular object. So we suck those into the system, into memory. We then read through the symbol table looking for any exported information. And if we export a symbol, we tuck that away, and I'll talk about that in a little bit more depth shortly. We also go through the relocation information for symbols, and we really relocate them according to the symbol type so that the addresses match where they are placed in actual memory. We also look for undefined symbols, so unresolved external references. And this is, again, something we've implemented that is probably not as general purpose as is necessary, but works for our particular instance. We take that information and we find these external references that we can't resolve, and we go and look through a global symbol table. And we will do a binary search because of the way the table is created, locate that information for that entry point, update the object within memory, and mark it as resolved. And so by the time this entire process is finished, we have a fully functional working object sitting in memory that the Mono system is able to access and use. If we were to find an external reference that we can't find, we resolve, we tell Mono, it prints a message, and we default back to the JIT rather than a ahead of time operation. So it doesn't break our application if this thing can't be resolved. We take note of the unresolved reference, and we try and find out why that is as it is. I'll talk about now the global symbol table that we've created that helps us resolve these external references. If you look through the symbol table of that .so we've created, you'll find things like memcopy, as you can see down the bottom there, marked as undefined, has a 0 address and an undefined type. So we go through and scan through our symbol table as part of the DL open operation. What we're trying to achieve here is the ability to create these shared objects without statically linking them. So when we run the AOT in JIT mode, everything's self-contained. There are no external references because everything's taken care of in the Mono runtime library. When we're running in LLVM or LLVM only mode, there are a heap of external references like printf, like memcopy, etc. there that need to be resolved. One option was we could have created the shared object as statically linked and linked them against the .a files that NUTX produces, in which case all these DLLs end up being unnecessarily bloated. We have multiple copies of memcopy sitting in memory and there. So our object was to eliminate this need to statically link by creating a global symbol table. We also necessitated the inclusion of the libc++ library at the runtime link because the LLVM only code has certain C++ dependencies. What the global table is simply a module called modlib_globalS.s created by a script. script search throughs of the runtime and the .a files created by the build process, filters out any unwanted entry points, sorts them so they're suitable for use by B-search. So here's what part of an excerpt of that table looks like. So at the beginning, we have all these names of the entry points, which we will then match during our search process. The table itself starts down here, a global table. It consists of a pointer to that name and the address within the NutX runtime where that symbol lives. In addition to the global symbol table, each module has its own dynamic symbol table. So as you saw earlier, mono underscore AOT underscore file underscore info was one such and probably the only exported symbol. And we keep that in a data structure associated with the module, such that when mono loads an ahead of time module, when it uses DLSym against that handle returned by DLOpen, we're able to find that symbol, and mono can then do its work of determining where all the methods live within that particular object. So we've got two things happening. We've got a global symbol table that contains all those typical libc functions that the AOT object may be calling, and we use it to resolve those at load time. And we also create a local module symbol table containing all the exported symbols of that particular object. At the moment, as I said, with mono, we only have one, but it's general purpose enough that if it has multiple, we were able to store them and keep them available. So a quick look at under the covers here, what's happening, what we had to add to NutX to achieve these things. And I won't get into too much detail because it's a fairly dry topic, but I'll try and hit the highlights of what was necessary to provide this particular function. Well, first of all, we needed a global offset table, and that needed to be added to our .ld file for the linker so that it can be present when we start doing PLT type things. We had to add some additional definitions found in shared objects, the load types, the program header types, etc., that currently weren't needed by NutX, but in our particular example, we needed to add them to support these dynamic objects. We needed to add handling of the R_ARM relative and ARM jump relocation types. These are fortunately very simple ones to add to the code. The code's nicely structured as a series of case statements. We just had to add our particular cases in there and have them added. For the DL functions, the library routines, we needed to do things like for the close operation, we had to make sure that the symbol tables that we created are freed so we don't leave memory hanging around. For the open, we needed to add some debug code. The existing DLOpen has a nice little debug feature where it will print a whole lot of debug information about the objects. We just added some more to cater for that, our particular cases there. And we also obviously needed to let it understand that there were things called ET DYN objects. We added new fields to the data structure that manages these DL-opened objects. We needed to keep information about the program headers and the exported symbols, etc., certain data section addresses that exist within a dynamic object, and some indexing information, because we're now searching through a number of different symbol tables. So we had to expand the symbol table lookup capabilities within NutX to help us with the global symbol table. The important things we added here within the definitions in modlibs.h was a couple of new prototypes for new routines we had to create. An insert symbol table and a find global operation, so that when we load an object, we created its own symbol table, and we were able to insert those into that table. And when we were resolving external references, we need to be able to find those things. So we added entry points there. The bind module, we were able to differentiate between the relocatable and dynamic objects. We extended the read sim to point to a given symbol table. As I mentioned, with dynamic objects, you can have multiple symbol tables, the dynamic symbols, the local symbols, etc. And we also needed to add a function that was going to go through and do the relocation of the symbols, much in the way that there is a similar relocate function for the ET-rel type objects. One of the major changes we made to functions was that we used the program header information rather than going through the section headers to determine how much memory we needed for the text sections, text areas, and the data areas for the object. So that was, as I mentioned, probably the biggest break from the existing processing that we performed. So notably, in ModLib sections, we no longer call it load S headers, but load headers to reflect that. So we use the programmer header information to extract important sizes and addresses. A lot of work happened in the symbol processing. We added exported symbols so that DLSim could look things up. We added offset information so we can easily locate symbols without having to go through and repeat calculations every time. We added this insert symbol to create a symbol table for exporting symbols so that Mono can find things that it needs in there, and adding a find EP to resolve those global table information. Freeing things on when we uninitialize a module at DL close time, verifying this is the first place it actually checks that the object you're trying to load is valid. So at the moment, it only checked for ET-rel. We now expanded that to say, look for accept ET DYN, and we'll handle them elsewhere. And of course, this global symbol table. And relatively ugly, the way it works, that we created it, but it works. And as I mentioned, expediency over elegance ruled in this particular part of my project. So the global symbol table is created by a script that traverses all the runtime. So it looks through the runtime.elf object, looking for things. It looks through the .a files created by the build. We use nm to extract the symbols. We have a filter to ignore other symbols that we're not interested in. So it's a fairly, as I mentioned, it's a relatively arbitrary process. It builds a sorted list containing the addresses of name and entry point information and builds that .s file. And then you rebuild .x with that symbol table the first time. So the first time you have it, you need a dummy module so that the build completes without error. Then you run the script and repeat, and this time the global symbol table has all that information that you're after. Is there a better way? Yes. A more elegant way? Yes. A more general purpose way? Certainly. But again, for the purposes of this project and being expedient, this global symbol table proved to be the easiest way to accomplish our task. So some final words, and you'll see this is a relatively quick presentation because the concepts and are relatively straightforward, though the code may not be. As you can see, there's about 2,500 lines of diffs created from the base LaTeX that we were using. It consisted of one new module and 19 changed modules. And you saw that through that list of other things under the covers there, what particular changes we hit. Again, what we're looking for in the future is to generalize it so we can support dependencies on other shared objects. So if we have a nesting of shared objects that require other shared objects will be able to handle it. We want to generalize it to other relocation types that may rear their ugly head. We also want to look and make sure that it works in all the modes of operation of NutX. At the moment, we run it in the mode that we build our particular runtime in. So does it run in flat mode? Does it work in X mode, etc.? We've purely concentrated on the way we do things in our particular environment. So we need to revisit, ultimately, and verify that conformance with coding standards, revisit and verify that it works in all the different modes of operation, that it doesn't break other architectures, that it doesn't cause all sorts of other grief for people. So hence why it's not available as a pull request. Ultimately, we'd like to be able to make it available to do so, whether we do it ourselves or just say, here's the code, would you like to work on this as a base, etc. That's the what we're looking for in the future. Again, if you're interested in the way that Meadow and that works, see if you can dig up Mark's presentation from yesterday from the video. I think it starts at the 7-hour 43 mark in the video. I went and revisited today because I think he spoke about 3 a.m. Australian time. And sorry, Mark, as much as I enjoy working with you, I wasn't particularly enamored about staying up that late. So with that, I will hand it back to the organisers and unshare.